Hi, everybody. Now we're doing section 1.7, which is one of the most important theorems in all of numbers. Actually, this we're calling it here, the textbook calls it the unique factorization theorem. This theorem is often referred to as the fundamental theorem of arithmetic. Um, I just want to mention as a side point, there are a few different theorems that are called fundamental theorems. The fundamental theorem of arithmetic, that's what this is right here. We're gonna get into it. The fundamental theorem of algebra, that's that a polynomial has n. You can factor polynomial to n roots, n distinct root, not distinct, but n roots. And the fundamental theorem of calculus, as you know, is that the integral is equal to the antiderivative, and these are some of the famous quote fundamental theorems. Anyway, this is very fundamental, and here's what it says: every integer greater than unity, greater than 1, can be represented in one and only one way, as a product of prime numbers. In other words, if you take a number and you make a factor tree, you're going to get a certain answer. Well, first of all, it's possible to make a factor tree and get a prime factorization of a number. Second of all, if two people do two different prime factor trees, you'll always get the same final answer. That's what it means. Only one way. That's what unique means. By the way, that's what the word unique. Unique means that there's only one. Okay, so we're going to show. First, we have to show the existence that there is one, and then the next part. Then later on, we're going to show that it's unique. So let's do it. So this is going to be pretty straightforward. We already established how to find a prime factor. So if we have a number m, we could say m is equal to some prime number times some other number m1. Now m1 might just equal 1, and then we're done. But if it's not doesn't equal 1, then I could take m1 and factor that, so to speak, and bring out a prime factor for m1. So m is equal to p1 times m1, but m1 is p2 times m2. And I can just keep on doing this. I can get an m2 and an m3 and m4, and these m's are going to get smaller and smaller. The only thing is, is a finite, m is some finite number. If I keep on going smaller, eventually I'm going to hit 1. I'm going to hit the bottom. It's like we had this argument earlier again, with positive integer natural numbers. If you keep on going down, eventually you're going to hit the bottom, similar to parachuting. So there you go. We have our prime factorization. So m is equal to p1, p2, dot, up to pr. I'm just saying pr. And all these p's, p1, p2, these are all, prime numbers. Prime numbers. They may be the same. They are all prime numbers. Now, that's the first part. That's the existence part of the theorem. Now for the uniqueness part. So let's assume that we have a number m, and we broke it down into these primes. And let's assume that we could break m, the same number m, down into some different primes, q1, q2 up to qs. Now s and r may or may not be the same number. There might be 20 factors here and 15 factors here. We don't know. We're not saying. But we know that we have two different prime factorizations for the number m. Both of these equal m. So what we're going to do is actually going to set these guys equal to each other, and have a party of cancellation. So we know that m, we did it. So we have m is equal to p1, p2 up to pr, and m is also equal to q1, q2 up to qs. And now we want to show is that the p's and the q's are all the same thing. That's what we want to show. I'm going to show that one by one. So we're going to start with P1 without loss of generality. We'll start with P1. Now P1 divides the left side of this equation, so therefore it has to also divide the right side of the equation. The only thing is P1 is a prime, and we know from the previous section that P1 we see P1. So we just check. Well, so if P1 divides these primes, it's got to divide one of the primes, which means it's going to wind up equaling one of the primes. So because that's the only way. P1 would be a factor of Q1, but the only way that could happen is if it equals Q1. So basically, we're going to take P1 and Q1, knock them out, and now we have P2, P3 up to Q2, Q3. Well, by a similar argument, I could show that P2 is equal to to some Q. I'm going to say Q2. By the way, I'm just making convenient. And then you knock that out, and you just keep on doing this ad infinitum until everything is knocked out, and finally it's just going to be identical, and that completes the theorem. And once we have this, typically when we write a factorization, I know that's how I always do it. We write P1 to the alpha 1, P2 to the alpha 2. We always write it, in that way, just to it's convenient. It's a convenient way to write it. So just for example here, if I would have 72, so that 72 is 2 to the third times 3 to the second. That's all. Anyway, let's see. Do I still have my? I lost my thing. Just give me a second. I'll bring it back. So what I was trying to say here is, boys, notice with computers, they always take a long time when you're waiting for them. So what I was trying to say is if you have a number like 72, so 72, so that equals 2 to the third times 3 to the second, for example, and that's just that's just how it works. So that's what it means when we say P1 to the alpha 1, P2 to the alpha 2, and so on and so forth. Alrighty, let's go back here. And now this is going to give us some very quick corollaries, not coronaries, but corollaries. So if A and B are relatively prime integers and C is divisible by both A and B, C is divisible by AB. So if A and B, in other words, if C is a common factor of two relatively, I'm sorry, C is divisible. So if C is a common multiple of these two relatively prime numbers, it's going to be a multiple of their product, which is pretty essentially in corollary, by the way. And if A and B are each prime to C, then AB is going to be prime to C. That also makes sense. And if there's no common factors, and finally corollary number 3, if A is prime to C and AB is divisible by C, then B is divisible by C. That's the only way it's going to work because it's not coming from the A, it's coming from the B. Alrighty, everybody. That's the fundamental theorem of arithmetic. It's fabulous. That concludes 1.7, and we'll continue with more exciting math as our heroes continue. Okay, bye, everybody.